Hi guys, BuildZoid here, and today we're going to be taking a look at the PCB of a recent addition. Well, it's not really that recent, but to it's definitely a new addition to my never-ending collection of GPUs. Say hello to the GTX 460 super overclock. So since this is a 460, it is very old and very irrelevant, but this is a super overclock edition from Gigabyte. So the PCB is kind of interesting, and that's kind of why I wanted to cover it. Now, at this point in time, this card is so irrelevant that it's actually really hard to find, I assume there's supposed to be some, overclocking tools for this card. Can't find those. And, other information about this card. Just can't get my hands on any of that. But, still, the PCB is very interesting. And because it's so old, it's actually still quite easy to vault mod, even if, it would be nice if I actually had all the utilities meant for this card. But still, anyway, let's get right into it. And as you can see, I have delidded the card, so that's just a case of, I just delidded it with a box cutter, as I do, because, yeah, that's, I'm not sure there's a better way really to do a GPU. I guess somebody could make like a custom delid tool for GPUs that would I don't know, screw into the PCB, and then, the thing is you'd have, ideally you want to be supporting the actual substrate, because you don't really want to be, exerting force, on the adhesive and the solder balls holding the substrate to the PCB, right? Because you could potentially break the connection between the substrate and the PCB, and then you'd have a bad day. So it's kind of one of the main risks with delidding a GPU is that, the other, if you're using any kind of blade method for delidding, then the other risk is that you're going to cut into the substrate and break it. So that's the other thing. But there's also the issue of, you could potentially, unlike with CPUs, you could potentially just break the connection between the substrate and the PCB, and then you're going to have a bad day, depending on how badly you broke it. So, yeah. Anyway, I did manage to delid it. It still works. So, yeah, that's kind of that. Just have to be careful doing it, and not use excessive force. Anyway, let's get into the VRMs, and there's a whole bunch of kind of interesting things around the card, because it is a super overclock edition. So we have a whole bunch of extra chips scattered around the card. Unfortunately, I've not really looked into what they do. I assume they're for enabling also this stuff over here. I assume all of it's for enabling various sort of overclocking features. To do with things like VRM switching frequency, maybe load line settings as well. I didn't really study the data sheet for that chip that much, which maybe I should have, but it's not it's not I don't think anybody really cares that much anyway. I also think we have voltage read points down here, just judging by the fact that we have these fuses right next to them. So I assume this point, that looks like it's probably ground. And then you'd have, why are there 4 fuses though? No, okay, that's probably not ground. That's going to be something else. Been ages since I've, this is so old that I actually don't know everything about these cards because they're so damn old, but hey, eventually, I'm sure over time I'll just probe everything on it and figure it out anyway. So, anyway, this is your vCore VRM, this right here. And then down here we have the memory VRM. So that's a single phase. The vCore is controlled by that chip over there, which is a ADP4100. That is a 6-phase controller from onsemi. So on semiconductor, so that's 1, 2, 3, 4, 5, 6. So yeah, we have a true 6-phase vCore VRM. We also have the drivers for it right here. Well, there's one. There's the 1, 2. One of them seems to be hiding behind that capacitor. So that's our vCore VRM. This chip supports VRM switching frequencies of 245 kilohertz, 500 kilohertz, and 800 kilohertz. Now, I'm assuming that this runs at stock at 245 kilohertz because these are, for the time, I do believe these were relatively high-end MOSFETs, but compared to what you get, these days, these are really slow. And so cranking up the VRM switching frequency to, you know, something like 800 kilohertz is actually really bad for the VRM efficiency on this thing. So yeah, that's one thing to consider. It's also why when I was doing my VRM efficiency calculations, I'm doing them both for 245 and 500 kilohertz, because I do not intend to, well, assuming this runs on 245, I do want to bump it up to 500, because increasing VRM switching frequency does tend to improve GPU core overclocking capabilities. Like, that seems to pretty reliably achieve that. So I do want to do that if that's possible, and I assume that might also be, like, I assume, because the way this controller, damn it, like, this controller right here, it's not digital, or at least it's not fully digital. I didn't really study the datasheet maybe as much as I should have, but their controller for the VRM switching frequency, that's just set by a resistor. So, you know, I assume maybe one of the chips on the back controls the resistance between a pin on the control, like the pin that sets the VRM switching frequency, and whatever that pin's supposed to be connected to through a resistor. I assume it's ground, but again, I maybe should have read the datasheet a bit more before going into that. But, you know, it's like the fact that the control exists is more important than how it necessarily works, as far as I'm concerned. So, because, like, I can just check, like, if you want, you can just check the datasheet. Seriously, if you just search onsemi ADP 4100, you'll get the full datasheet for the chip. I assume this would also be found on some other GPUs from that era, so, you know, it might be a useful chip to know stuff about. So, that's that. Anyway, so that's our controller, and I don't really know how it compares to, like, other controllers of the time, because this is old, and not like this. I got into PC building around the GTX 500 series of NVIDIA GPUs. So, like, this whole thing is just like, I have no idea. I have no idea how this compares to anything at the time. So, I'd assume it's relatively high end, because 800 kilohertz switching frequency, like, modern controllers can go up to like 2 megahertz. But those tend to be pretty expensive. Well, actually, these days, today you can get a controller that goes up to 5 megahertz on 10 phases, which is, like, that one's really, really new. But, yeah, so I don't know. For the time, that seems like it was probably relatively high-end. But, again, that wasn't paying attention at the time, so I don't know how this compares to other GPUs back then. Anyway, so that's our controller. Oh, and it supports up to 1.6 volts vCore, up to 1.6 volts over a parallel vid interface. So that's basically, there's several different pins, and each pin corresponds to a bit. Depending on the bits that you set, you get a different output voltage. So yeah, that's a pretty standard voltage control scheme for old GPUs. And I assume it's probably those resistors right there. Anyway, so theoretically, if you wanted to do voltage control without, like, skewing the control circuitry of the ADP 4100 here, you would actually just use a dip switch. That's assuming, like, a multi-channel dip switch. That's assuming you can't, like, I'm not sure that I'll find the software for controlling this card. So I'm not sure. If the software control is good, then great. I don't need to do anything for that. I'll probably still have to mod the switching frequency. But if I can't find any software, then yeah, I have a card where we have a parallel vid interface. I really want to have a card with, like, I've never done a dip switch based voltage control mod, so here, another card that I can try that out on. I also have a GTX 780 Ti that I want to try it on. So anyway, on to the actual VRM, which is probably the part that people are more interested in. So for the vCore, well, actually for vCore and MEM, the MOSFETs are all the same. So we have 2 low-side MOSFETs in parallel and 1 high-side MOSFET. And as I said earlier, these are actually rather slow. So the high-side MOSFET is a 70... It's a PH 7030 AL from NXP. So that's an Xperia semiconductor. And these are 7.9 milliohms. So that's not, like, compared to modern high-side MOSFETs, that's pretty high. You can find certain, like, for example, the Texas Instruments CSD 87350 dual NFET, which is really popular with a lot of motherboards and GPUs. That has a high-side MOSFET that's like 5 milliohms, if I remember correctly. So this is pretty high, but if you look at like more mid-range GPUs, then around like, well, the 4C, so that's 7.9 milliohms at 10 volts gate to source. But if you look at something like a 4C10N from On Semiconductor, which is really popular for a lot of sort of mid-range, even, yeah, mid-range to low-end GPUs these days, that actually has a 6.9 milliohm. That's a 6.9 milliohm MOSFET, and that's normally used in the high side as well. So this is, it's kind of high, but, you know, not a huge difference. But where the huge difference comes in compared to like modern high side MOSFETs is that this thing takes 38 nanoseconds to switch on, and then another 21 nanoseconds to switch off. Now, that's according to the datasheet. Depending on what driver you're actually using, you're going to get something different. But I couldn't identify the drivers here, and it also depends on the gate extension resistor. And part of the issue is that I assume this package has, because like one of the things that improves MOSFET rise and fall times is actually having a lower inductance package for the MOSFET, so that you can drive the gate really, really quickly without having ringing issues. And the thing is, I do believe that with these, that is kind of the limitation. Like the rise time is kind of limited by the packaging here. So yeah, these are pretty slow. Like these days, if you look at like a high side, a really high end high side MOSFET, you can even see single digit rise times if the driver is strong enough to do that. That's the other concern, right? If the driver's not fast enough, then the fact that the MOSFET could switch at 5 nanoseconds is kind of irrelevant if the driver can't supply that much current to it that quickly. So yeah, but this is slow. This is really, really slow, and it's one of the main reasons why I wouldn't mod this VRM to run at 800 kilohertz, because the VRM efficiency would just fall off a cliff. I mean, already at 500 kilohertz, it's not going to be great, but at 800, it's really bad. So yeah, that's our high side MOSFET, and then the low side MOSFETs are 34. Damn it, PH. Make your life easier Googling them. Without the PH, these are a bit harder to find. So 3430 ALs, and that's a 3.5 milliohm RDS on. And if you're wondering, like, if you go into the datasheet, this is actually the maximum RDS on as well as that is, and that's just because for most MOSFETs, I take the maximum RDS on. At 25 degrees junction temperature. So anyways, 3.5 milliohms, 10 volts gate to source voltage, and they're low side MOSFETs. So these are generally always kind of slow compared to high side MOSFETs, but 50 nanoseconds rise time and an 18 nanosecond fall time. That's, again, you know, restriction of how quickly you can drive them. So this one actually does have, like, this has more gate capacitance than one of these. It's just that if you have a strong enough driver, you could still manage to drive it faster than, say, this under ideal test conditions. So in reality, it would probably be even slower than that on the, well, again, like, it really depends on the driver used. So that's kind of that. But these are slow as well. These days you can get sort of low side MOSFETs that are like 30 nanoseconds, and that's for like 1.4 milliohm resistance low side MOSFETs. So like half as much RDS on and still quicker to switch on and off than what you have right here. So yeah, the like old MOSFETs, they're slow. That's one of the main differences with the modern ones. The RDS ones haven't, well, the RDS ones have improved, but mostly it's just like you can drive the modern ones much, much faster. So that's kind of that. And the end result, like, that's why I really think that this probably runs stock at 245 kilohertz VRM switching frequency. Anyway, for the VRM efficiency, what that means is it's still not that bad, because I did all the calculations at 245. But we're going to be looking at 1.2 volts output, 245 kilohertz switching frequency, 10 volts gate to source voltage, because, well, if we ran these on 4.5 volts, they would be worse. 245 kilohertz switching frequency, 10 volts gate to source. And at that point, we're going to be looking at 100 amps output at about 16 watts of heat. And what's that? That's not 16 watts there. 150 amps output at about 29 watts of heat. 200 amps output at about 45 watts heat output on the VRM. So at this point, it's like I want a heatsink on these MOSFETs, but I'm not sure a GTX 460 can actually hit that much current pull. Consider it, well, no, it probably can. On liquid nitrogen, it probably can. And then going up to 250. So I go all the way up to like ridiculous levels, because theoretically, if you have enough cooling, one of these can actually handle a ton of current. The main issue is that, well, there's several of them in parallel, and you're going to end up with a lot of heat output anyway. So still 250 amps, you're going to be looking at about 64 watts of heat output, and then going all the way up to 300 amps, you're going to be looking at about 86 watts of heat output. And that's all for 245 kilohertz. If you go up to 500 kilohertz switching frequency, and I've just realized that, well, is it that bad? It's not that bad. Yeah, the orange shows up okay-ish. 100 amps at 500 kilohertz, you're going to be looking at about 26 watts, right? So that's what I was saying, is just like, you lose a lot of efficiency because these MOSFETs are so slow, and the speed of this one primarily, the speed of the MOSFET switching on and off directly translates into just extra energy losses every time you turn it on and off. So the longer it takes to turn on and off, the more power you lose every time you try turn it on and off. So that's kind of that. And so at 500 kilohertz, your on-off, like your switching losses literally basically double over what you have at 245 kilohertz, right? So that's why the efficiency kind of falls off a cliff. Then going to 150 amps output from 29 watts, it gets to 44, right? Then from basically you can take the value over here and shift it that way, which actually literally happens at 200 amps, where this hits about 64 watts, and then 250 amps hits about 88. So at this point, it's actually worse than what you'd have at 300. And then at 300 amps, it goes up to 115 watts. So essentially, it's like making the VR, like going from 245 kilohertz to 500 kilohertz. Did I just break? I just broke GIMP, didn't I? Oops. Undo, damn it, you stupid program. Undo. There we go. Anyway, so yeah, it's essentially like, you know, if you had enough cooling capacity for 200 amps at 245 kilohertz, then you've basically chopped yourself down by 50 amps output capability by increasing the switching frequency, which is why, like, initially I'm going to just run the card on 245 kilohertz, and then if we, you know, if it doesn't seem to be doing too badly on VRM thermals, then we can try out, see if it does any better on 500 kilohertz in terms of overclocking. But yeah, the efficiency decrease is quite drastic. And yeah, the orange really doesn't work that well on the blue background, does it? Oh well. Whatever. Too late. So that's the vCore VRM. And then the memory VRM is a single phase, and that's controlled by that chip over there. And that is an NCP... Oh, I don't get why my handwriting is so much worse today. There we go. NCP 1587. And that, well, there's two variants of this chip. There's one that does 200 kilohertz and one that does 275. I'm just going to assume this is the 275 kilohertz variant, which is the 1587A. And the reason why I'm just assuming this is the 275 kilohertz version is because this is memory power. It doesn't really need to move that much current. So, you know, if we're going to be... I'm not sure what voltage this normally runs at stock, but ultimately I do plan to bump it up to at least 1.65s, if not 1.65 volts, if not higher, if it's running at 1.5. So 1.65 volts, 275 kHz. Oh, and that's a single phase voltage controller right there, obviously. Integrated drivers and everything. Like, that's normal for these chips. Like, chips that look like that normally integrate the driver, and they're pretty dumb. So, and they're popular for single phase memory or memory controller rails and that kind of thing. So, Anyway, 1.65 volts, 275 kilohertz, 10 volts gate to source, because of course, like, what else would you run these with? And for 10 amps output, you'd be looking at about 1.5 watts of heat output on the VRM. And then for 20 amps output, it would be producing maybe about 4 watts. So yeah, quite a drastic increase in heat output. This should still be like doable in terms of cooling, right? And then 30 amps output, you'd be looking at about 7 watts, which like still really isn't that much of a concern compared to the VCore VRM above it, right? So it really just depends on the heat sinking for this VRM. And I do actually intend to just somehow get heat sinks on here. Probably just... I wonder if I have a heatsink large enough to cover all of them. Well, we'll see. We'll see. I'll figure something out. Since there are holes here, it should be relatively easy to just use like, well, just use like a single core piece of wire to hold the heat sinks in place. That's what I usually do when I have a GPU, because I actually got this without any VRM heatsink, which I think at stock, like that like at stock settings, that probably makes sense, because you know, if you just force enough airflow over the VRM, it should be fine. It is relatively capable. It's just like within what I assume would be the stock current draw for a GTX 460, that really shouldn't have a problem as long as there's airflow over it. But yeah, once you really start pushing it, the fact that this doesn't have a heatsink is actually kind of concerning. So yeah. Anyway, that's the VRM efficiency on here. For the main rails, we have a PEX VRM down here, which this is just a 3 amp integrated buck converter from Anpec Electronics, which is a APW 7145. There is a public data sheet for that, so I'll maybe vault on that. I'm not sure how much this rail does on this generation of GPUs. It varies a lot. I know on some GPUs it's super, like on some NVIDIA GPUs this is super useful. On other NVIDIA GPUs it does absolutely nothing to adjust that. But yeah, so that's that. Other than that, we do have some shunt resistors around the card, so it does look like it has power monitoring. Though I'm not sure. Well, worst case scenario, I'll just have to mod those as well to disable any power limits that the card might have. Now I want to talk about some of the other interesting things about this card. So if you're like me, right, and you look at this PCB, this right here is a big, what is that? Why is it here? There's no obvious, like, there's no large regulator near it. I mean, there's this one right here, but that's unnecessarily far away. There's that. I assume that's a regulator. I'm not sure, but that looks like a regulator of some kind. There's this right here, which, again, that's a bit far away. If we look at the back of the card, there's really, like, those are the legs of the capacitor. There's really not anything, like, near it, right? That would be like, okay, that makes sense. So actually what's going on with that capacitor is it's... So this capacitor right here is actually vmem. So that's on the memory power plane. And I assume it's because like the memory VRM is all the way down here, right? And our last memory chip is all the way over here. So if the memory chip over here suddenly needs a lot of power for some reason, it's going to take a while for that power to, like, it would potentially take a while for that power to get to it from here, right? So it just makes sense to put an extra bulk capacitor over here. And you see this on some cards. Not everywhere, but especially like more extreme overclocking oriented cards like an SOC series card. Like you'll see this where the memory chips really far away from the memory VRM will actually have extra capacitors near them. Though I've never seen a case where it's like a straight up aluminum like where it's a I assume that's a polymer. It might be an electrolytic. Well, polymer capacitors are technically still a type of electrolytic. It's just that the electrolyte's solid instead of a liquid. But still, it's like normally you don't see something this big. Like normally you'd see a couple more multi-layer ceramics. But no, this is actually just for memory power. So this is something I've done also when I mod GPUs, where I'll just whack an extra bulk capacitor next to the memory chips really far away from the memory VRM. So Yeah, Gigabyte does that for you here, though I think I'll still still build on top of what they've done here already. And then I assume all of these are also going to be memory, power, multi-layer ceramics around here. And if we go on the back of the card, on the back it actually looks quite normal, I would say. Right, we have all of that. If you're wondering about... On the back of the card... GIMP, why are you being stupid? Stupid program. Anyway, if you're wondering about these, those are actually for vCore. So, yeah. Those are bulk capacitors for vCore. Well, not really bulk because they're tantalums, and at the time I assume tantalums had a significant advantage over your typical, cylindrical... I'm still going to say they're polymers. I'm just going to assume they're polymers and roll with it. I might be wrong about that. But normally these would have a frequency response advantage over your CAN-type capacitors, regardless of if they're polymers or not. And these days you can get SMD polymers, which are actually superior to SMD tantalums, at least when it comes to frequency response there. So yeah, but these are on vCore, so they're basically there to help, filter out transients from the GPU core, as well as any, lower frequency switching noise. That's kind of what they're there for. We also have one of these, which is a I'm not going to even try to pronounce that. That is and that's like a predecessor to the, well, actually, I think at the time they already probably had aluminum polymers in SMD packages, but basically the idea behind these is that they're supposed to replace all of this. In practice, there are some laptops that do that, where they just use one of those right behind like a GPU or a CPU. But if you look at a lot of extreme overclocking cards from the era when these were still produced, I don't think they make these anymore, or if they do, they're not popular anymore, because one of the main issues with these was they're not very high endurance and they tend to fail over time. But at the time they were relatively popular for extreme overclocking cards, but they wouldn't actually ever put them right behind the GPU core. And I assume that's probably because a ton of multi-layer ceramics just works better than this. But you would find cards where they would just sort of whack that right after the vCore VRM like we have here. There are cards where you'd actually find several of them. I think I have a GTX 580 classified sitting on a desk over here. And there's 3 of those on that card. So, yeah, at the time these were pretty popular. So the idea behind these is that they combine a very high total capacitance with a really great frequency response because they're in this, because of the packaging they're in. And the idea was like, yeah, you could totally try replace all of your multi-layer ceramics with one of these. But extreme overclocking cards would just use them as extra bulk capacitance with better frequency response, though. With how far away this is from the GPU core, right? Like, the thing with the high-frequency filtering is you really do want to cram it as close to the thing you're filtering. So this is a bit far away from that. But still, it's a cool piece of sort of capacitor technology that these days you don't see anymore because you can just get better capacitors in normal packages with better endurance. And yeah, but at the time, this was like the highest end of... I assume these are polymers, of aluminum polymer capacitors that you could get. So those are pretty cool. So you have that. And I think that covers everything on this card. I don't think it has dual BIOS. There's definitely... Is there? Is there a BIOS switch? No, there isn't. Yeah, so I don't think it has dual BIOS. But it looks like it could have had dual BIOS. But... yeah, that's the GTX 460 Super Overclock, and it's kind of neat. Like, that's all there really is to it. And yeah, it's kind of a shame that we don't get mid-range cards these days that go this far to be like a extreme overclocking geared mid-range card. But the thing is, these days it's kind of like, unfortunately, with the way 3D benchmarking has progressed, these days you just like, you either have a 2080 Ti or you're irrelevant. That's kind of how it works, right? If you want to do any 3D benchmarking, your other option is to just benchmark old GPUs like a GTX 460 or something like that. So that's why I picked up one of these, is like, it's worth decent points on HW bot, but also because like this is actually a really cool PCB with that, the random bulk capacitor over there. I mean, it's not random, it's very intentional. It just looks kind of random. The V-Core VRM that it has, like, yeah, I really wanted one of these because it's like, oh, it's a cool super overclock series GPU from Gigabyte. And yeah, so that's it. I mean, there's not really much else to say about it because you can't buy it these days. So hopefully this was interesting. So I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. And if you'd like to support what I do here with actually hardcore overclocking, which includes, you know, buying ancient GPUs on eBay just to add them to my collection on the hopes of someday I'll run it on the Sub-Zero cooling. I have a Patreon and a Teespring. You can support me through both of those. There's links to both down in the description below. And yeah, that's it for the video. Thanks for watching, and goodbye.